Section 4.6, Graphing, Calculus, and Calculators. For our first example, let's graph this polynomial and use the graphs of its derivatives to estimate all maximum and minimum points and intervals of concavity. So we pull out our handy-dandy calculator emulator, go to y equals, put in 2x to the 6 plus 3x to the 5th plus 3x to the 3rd minus 2x squared. And let's hit graph. Alright, so we get this interesting looking graph. So from our graph, it seems like we hit some minimum around here. It's a little bit cut off. And then it goes up infinitely on the left and right. We can maybe see this if we zoom out a little bit. Let's try doing that. Yeah, so it does seem to be a minimum right around there where it's getting cut off in our zoomed in picture. So let's see if we can estimate where that would be using the derivatives. So let's go back to zooming standard. Get our graph that we had. Let's go to y equals and let's put in the derivatives. Well, if we differentiate this guy, how about we could do that over here for a second? We get that the derivative by the power rule is 12x to the 5th plus 15x to the 4th plus 9x squared minus 4x. And if we differentiate it again, we would get that this second derivative is 60x to the 4th plus 60x to the 3rd plus 18x minus 4. So let's put those in our calculator now. It's 12x to the 5th plus 15x to the 4th plus 9x squared minus 4x. And while I'm here, I'll put in the second derivative too. 60x to the 4th plus 60x to the 3rd and plus 18x minus 4. Okay, I just want to graph one of these at a time now. So how about we turn off the blue graph and we'll turn off the black graph and just get our derivative, the red one. Okay, so it looks like it goes from decreasing over here to increasing because it goes from negative to positive. Then it goes over here. Let's see if we could zoom in and see what's happening over there. Oops, it looks like we left our black graph on. Let's turn that off. Okay, so it looks like the derivative goes from negative to positive, then back to negative, and then back to positive. So we should have, if we're going from negative to positive, we're going down then up. So we should have a minimum over here, and then we should have a maximum over here. So going back to our original graph, that means there's a maximum over here that we didn't notice. So let's pull up this right over here. That's for our derivative. And let's go back to our blue graph. Let's turn that back on. And let's turn our derivative graph off. We can see the zoomed in version. There is a little bit of a thing over there. So let's hit zoom to zoom in. Yep, so it does dip. We just didn't notice. So let's pull that off. So we could estimate using both of these graphs pull our calculator away for a second, that how about f of, let's say, minus 1.62. Say that's around where this thing is, right? And let's say, well, definitely f of 0 is 0. That's a local max. But for our other min, how about over here? Say like roughly over there, maybe that's like 0.35. So f of minus 1.62, which we could plug in to see is about negative 15.33. And f of 0.35, which is about minus 0.1, those we're estimating our local minimums. You can also see that those estimates can be made a little bit better using the calculator. If I disable this function, I go into my derivative, I go to the graph, I'll zoom out a little bit. I go calculate the zeros. So let's take second calc 2 zeros, because I want to know exactly where the derivative changes from negative to positive. So if I go to the left and then the right, and then I guess where it is, that's how I can get 0.35 for the x value. If I don't just want to eyeball it. But again, it's not super important right now because we're just trying to get rough estimates using our graphs. Oh, we almost forgot. F of 0 equals 0 is a local max. Okay, so let's say this was the graph of f prime, this was a graph of f, and this was a graph of f. So we still haven't gotten the graph of the second derivative yet to get our intervals of concavity, so let's do that now. Actually, let me go down a little bit, get some more space. Okay, so for our second derivative, let's turn off the derivative and turn on the second one. Let's go to graph. Not so great. How about we zoom out? Zoom out a little more. Alright, very hard to see, but it looks like it goes down and then up. So we'll zoom back in. Maybe it's about as good as we're gonna get. So it looks like if it goes from positive to negative over here, and then negative to positive over here, that we have inflection points here and here, where it will change concavity. That kind of makes sense. If you look at the original graph, it looks like there's inflection points around over there. Let's say it's changing inflection around over here to go from concave up to concave down. Let's see. Actually, it looks like, I think it goes like down over here, goes up, and then changes concavity right around over there. And then it goes concave down, and then it changes concavity again. Like over here, you could more easily see that it goes concave down, and then switches concavity around over here, and then goes concave up. So we could estimate that by getting the zeros of this thing. So how about we do that? Second calc. 2 is the 0. For the left, let's go around over here, so it looks like I should be like negative 1.5 or something. 1.9, whatever. I just need to be to the left of it somewhere. And then let's go to the right of it, so how about we go around over there, and then we'll guess a little bit to the left. Okay, so it looks like we have a 0, like negative 1.23. For the other one, it's around like over here, or somewhere over here, sorry, that's the minimum. So around over here would be our next inflection point, which is like around over here somewhere. So we could say that that's like 0.19. So how about we say that f is concave upward, on minus infinity to minus 1.23 union 0.19 to infinity, and f is concave downward on, let's say, minus 1.23 to 0.19, that small amount in between. Alright, so let's retrieve this really quick. And we'll say that this is the graph of f double prime. Notice that no single graph really represents our function. If we were to just go off of this original graph, then we would have totally missed this minimum over here and this maximum over here. So it was important to draw multiple graphs. If we just use this one, then we would have missed this minimum over here, which we couldn't have even seen if we didn't zoom out a little bit first. So we really needed our derivatives to help us understand that there would be some missing components in our original graph. Okay, let's draw the graph of the function f of x equals x squared plus 7x plus 3 over x squared in a viewing rectangle that contains all the important features of the function. And then we'll estimate the maximum and minimum values and use calculus to find these values exactly. So we pull back our calculator. We'll clear our other functions. And let's go and plug in x squared plus 7x plus 3 divided by x squared. Now let's reset our zoom to standard. Okay, that looks pretty good actually. How about we grab that? Yeah, that's good. So it looks like we have a local minimum over there. And it looks like we probably have an asymptote over there. We could double check this by looking at our function. Hitting zoom 3 to zoom out a little bit. And then going back up over here. Yeah, it looks like there's an asymptote over there. Okay, so it looks like around over there, let's say f of minus 0.9 would be the local min, which we can plug in to see is about negative 3.1. If eyeballing is not good enough, you can go back to your calculator, you can press second calc to get 3 is the minimum. You go to the left of it a little bit, you go to the right of it a little bit, and then you go in the center, and it says that it's about negative 0.85714, which is, yeah, negative 0.9. And you can see that the y value is about negative 3.1. Let's see if we can actually calculate what this minimum should be, though. Let's look at what the derivative of f is. So f prime of x, if we use the power rule, we could just divide each of these separately. Well, that derivative will end up being minus 7 over x squared, because the x on top, and then minus 6 over x cubed. So that simplifies to minus 7x plus 6 over x cubed when you find a common denominator. So let's see where that changes sign. It looks like we have it undefined at 0, so that's a critical number. And we have it equal to 0 at negative 6/7. that's when the numerator is 0. So that's another critical number. To the left of negative 6/7, the top will be negative, then this will be negative, so it'll be positive, but then the bottom will be negative, so it's negative. Then to the right of negative 6/7, the top will be positive, the bottom will be negative, and then this thing's negative, so it'll be positive. But if we get a little bit too big, then the top and bottom are both positive, so this negative makes everything negative. So it goes down, then up, then down, decreasing, increasing, then decreasing. So that tells us that at negative 6/7, which if we evaluate it is negative 37/12, is a local minimum. Because it goes down, then up. And let's estimate some concavity. So it looks like if we were to go over here, it's concave down, and then it switches and becomes concave up the entire rest of the way. So we could write that f is concave upward on minus 1.3 to 0. Not what I wanted to write. Minus 1.3 to 0. And then from 0 to infinity. So everywhere after, wherever it's defined, it's got that asymptote at 0. Then f is concave downward everywhere before then. So from minus infinity to minus 1.3. We're just estimating, so we better actually calculate this using our second derivative. So by power rule again, we get 14 over x cubed plus 18 over x to the 4th, which simplifies to 2 times 7x plus 9 over x to the 4th when we find our common denominator. So let's see where this changes sign. Well, it looks like it happens at negative 9/7, because that's when this thing's 0, and when it's undefined, it's 0. So before then, it's going to be negative, because the bottom is never going to be negative. Then it goes and becomes positive, because if we have a number that's to the right of negative 9/7, then that makes the numerator positive. But then any positive number will make both positive also. So it's concave down and then concave up and concave up, exactly as we suspected. So now we have an exact value though. We can say f is concave upward on minus 9/7 to 0, union 0 to infinity. And f is concave downward before then. So let's try graphing this function. We'll pull out our calculator again, go to y equals. This time we'll plug in x squared times x plus 1 cubed, divided by x minus 2 squared times x minus 4 to the 4th. Go to zoom, standard to reset things. Okay, so that's interesting. Let's grab that. Looks like it goes up and then down. Try zooming out a little bit. Still kind of hard to see what's going on over there. How about we zoom in but we change it so that we could see up higher. So go to our window, and let's change the y maximum to some big number like 500. Ooh, now we can see what's going on. Let's grab that. So it looks like it goes up, and then it goes down, has a minimum, goes back up, and then down again. However, if we look at our function itself, it seems like there's something going on over here at -1, because it should be 0 over there. So there should be some behavior over there. However, notice there's a cube by the 0. So it has to cross the x-axis. So that means that we're missing some information here. Let's see if we can zoom in on that area. So let's go to our window again. We'll change x now to go from, instead of, let's say, -10, how about we make sure that we see everything? We'll go -100. We'll go up to 1. We just want to see it near -1, really. And then everything around it. And we want to zoom in a lot. So how about we make y go from -0.05 to 0.05. Okay, so that does definitely give us more information that we didn't have before. Looks like over here, which we can't even see on this graph or this graph, but if we zoom in, we can see it dips down and then it goes back up. Let's try zooming in even more. We'll go to our window, and this time we'll make it x. Let's go really close to that 0. So -1.5, how about, to just past it at 0.5. And then for y, we'll zoom in even more. So how about -0.0001 to 0.0001. Now we can really see what's going on. So put our calculator back. I think that's enough information. It looks like if we look at this graph, it goes up and then down and then up. Sorry, down, then up and then down again. If we look at this graph, we can see that it goes down and then up. And then if we zoom in even more, we can see that the way it goes up makes it jump up a little bit, have a little bit of a local maximum. So if we want to try to actually draw this function, we need to kind of put all of these graphs together into like one super graph. So it should go something like this, where it has this asymptote, it goes down, then it goes like up, and then flexes and goes up. Oops, I didn't draw that very well. Try again. Down, then up, and then it like stays there a little bit, then it goes up, and then down, and then oop, and then up, and then it has an asymptote, and then it has a minimum, and then another asymptote, and then it goes down towards this one. So that could be x, that could be y, and let's say that this was over here, so that's at -1, so then this is at -1, and then this is at 1, our asymptote's at 2, so I'll put in a 2, and then over here we have 3, and then over here we have 4. So you notice this kind of hybrid graph that you get can only be done by hand. You could never get all of these viewpoints at once to show you the behavior if you were to do it using a calculator. You need to kind of combine all of these different graphs. Let's graph the function f of x equals sine of x plus sine 2x. We want to look at it from 0 to pi, it looks like, to estimate all the maximum and minimum values, intervals of increase and decrease, and inflection points. So we go back to our calculator, and we'll change this to sine of x plus, where is it, sine 2x. This time for our window, we want to go from 0 to pi. So there's pi. And we want to go from, well, the biggest sign could possibly be is 1, the smallest it could be is 1. So how about we go a little bit more than that? Let's go like from minus 1.2 to, let's say, 1.2. Okay, cool. So in order to make sure that we got that entire graph, let's go and calculate the derivative. So the derivative, using the chain rule, is cosine of x plus sine 2x times derivative of inside, so it's times 1 plus 2 cosine 2x. Do chain rule a couple times. Okay, if we were to use this, we could see that it looks like it's going up, and then down, and then up, and then down, and then up, and then down. So how about we actually take a look at that derivative? Let's try putting the derivative into the calculator. So we get cosine x plus sine 2x times 1 plus 2 cosine 2x. Okay, make sure the top graph is off and regraph. Alright, looks like we start out positive, then we become negative. So there should be a maximum over here. Then negative to positive, so minimum. Then maximum, then minimum, then maximum. Let's see if we can calculate some of those. Second, calc, 0. How about we do the first one? So it's going from positive to negative, so it should be increasing before then. And then it has that maximum over there, about 0.6. Let's pull this over here. We'll put this back. Oops, did not mean to do that. No, stop it. Okay, let's grab this, put it over there. So using this graph, how about we estimate that our intervals of increase are from 0 to 0.6, from 1.0 to, let's say, 1.6. That's around over here, up until over here, and from 2.1 to 2.5. We can then say that our intervals of decrease are from 0.6 to 1. They're just in between all these guys, 1.6 to 2.1, and from 2.5 to the end, which we said was pi. So then we have a local max each time it changes from positive to negative. So that's at 0.6, and the f value is about 1. It's at 1.6 when it's about 1 again, because sine, the most it can be is about 1. And then 2.5, which is about 1. And we would expect that the smallest it can be, it looks like in this case actually doesn't go to -1. Smallest it can dip is like shortly below 1. So let's say 0.94, which you can also get by plugging in. So f of 1, about 0.94, and f of 2.1 is about 0.94. So that's these two minimums. So we have these three maximums, and those correspond to 1, 2, 3 zeros, and then the two minimums, 1, 2 zeros, when it goes from negative to positive. Let's look at the second derivative now, because we want to look for intervals of, the inflection points. So if we calculate the second derivative, it's a bit of a mess. We get 1 plus 2 cosine 2x squared sine of x plus sine 2x minus 4 times the sine of 2x cosine x plus sine 2x. And you can plug this into your calculator. It's kind of a complete mess, but you'll see that this thing has zeros where this thing has inflection points. So we'll end up with a whole bunch of inflection points, which makes sense looking from the original graph. Inflection points from at 0, 0, at 0.8, 0.97, at 1.3, 0.97, at 1.8, 0.97, and at 2.3, 0.97. Let's go back to our original graph. Go to y equals, turn this one back on, turn the other one off, go to graph. This was our original function. It looks like we could probably extend this now because we've seen every single point is contained in this. There's nothing really missing here. So we go to window. Instead of going from 0 to pi now, how about we go from minus 2 pi to 2 pi. So it looks like this was our original graph. It just repeats itself underneath, and then it repeats itself like this. So it's nice and periodic. Okay, for one last example, let's see how the graph of 1 over x squared plus 2x plus c varies as c varies. Well, we'll pull out our calculator, and we'll go to y equals. We'll clear these, and we'll plug in 1 over x squared plus 2x, but we can't plug in c, so we'll have to choose some value of c. How about we choose 2? And then we can choose some other ones when we want to switch things up. We'll go to zoom, standard to reset it, and we get that graph. Okay, it's not so great. Let's try changing our window a little bit so we can zoom in. Well, that's a little better. It'd be nice if we were a little bit farther to the left. It looks like we really never need to go past round 1, so we could probably go from 2 to 2 for the y. So let's change our window. Let's go to like -5. Let's say up until 4. And for y, that looks like it should be about good. Let's graph that now. Okay, we'll pull that out. So that's at c equals 2. Let's do another c value. How about, let's say, -2. Oh, wow, it's totally different. Let's pull that out. So notice that x squared plus 2x plus c, let's take a look at that really quick, that quadratic. If we have x squared plus 2x plus c, well, we could use the quadratic formula. We could solve for where this thing is equal to 0. And we could see that that makes x equal to -1 plus or minus the square root of 1 minus c. So that's when this denominator is 0. So it looks like we should get asymptotes whenever we have c is less than or equal to 1, right? This implies that we get asymptotes for c less than or equal to 1. If c equals 1, then x is just -1. So we get an asymptote. We get one asymptote there. Notice over here we have 2 asymptotes because we have plus and minus. But then if c is bigger than 1, then we're subtracting more than we can. So this is not, there won't be any intersection over here with the x-axis. There won't be any 0 there. So let's see if we can take a look also at our derivative. Well, if we differentiate, we get negative 2x plus 2 over x squared plus 2x plus c squared. So if I look at our derivative, the only potential issue is at -1, right? Because the bottom is always positive. If I look at, well, minus, if I go to like -2 or something, then it looks like our top should cancel because I have minus over there. So it should be positive, so it's increasing over there. And then to the right, it is decreasing. You could just plug in like a 2 or something and notice that the negative is going to make anything negative. So this means that f of -1 equal to 1 over c minus 1 is a local maximum when c is not equal to 1, obviously, because then it'll be undefined. So we can get a couple more pictures here. Remember, this was c equal to 2. This was c equal to -2. Let's get our calculator back. And how about we get c equal to -1? Very similar to -2. Let's also get c equal to 0. Oops. I'll just plug in 0 over there. And how about c equal to +1? Okay, so we have one asymptote. And let's we graph one more other than c equal 1. We can do c equals 3 to go a little bit past 2. Okay, so let's organize these a little bit to make ourselves a little slideshow. How about we put this, too much, over here, let's say. Now let's move these down. I think I'm going to just be lazy. I'll erase this and fill these in. So this was c equal to -1, c equal to 0, then c equals to 1, and c equals to 3. Combining all of those with when c equals 2 and -2, we can see our 2 asymptotes, then become 1 asymptote, and then become 0 asymptotes, not even draw over there. And then this thing steadily gets flatter and flatter as time goes on.